Okay, welcome to the DDPS seminar today. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk unless you have clarification questions. If you do one, you are welcome to unmute yourself and ask those questions. Otherwise, please use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Therefore, of course, no classified discussion is allowed, so please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now let me introduce our speakers today. Actually, we have two speakers today. It's an honor to host two speakers. The Tobias and Alvaro will be our speakers today. Both of them are from DeepMind, the famous AI company, also known as the creator of the AlphaGo player who defeated a human professional Go player, Lee Sedol from South Korea. Alvaro is a research engineer at DeepMind, focusing on applying graph neural networks to physical simulation and reinforcement learning. Alvaro has background in physics and computer engineering and got his PhD at Imperial College London in 2017 in experimental ultrafast physics using X-ray free electron lasers, so-called XFEL, including applying machine learning to improve XFEL diagnostics. Tobias is a research scientist at DeepMind also. They're currently working at the intersection of physics simulation and machine learning. His background is in physical simulation for computer graphics, and in his PhD in Zurich and postdoc in Berkeley, he studied turbulent fluids, fracture, and closed the simulation, and wrote the fluid solver, which is now included in Blender. Maybe he can talk more about the Blender today. But Toby and Alvaro will present today the learning physical simulation with graph network, which is a very exciting topic. So please enjoy and expect a wonderful talk from Toby and Alvaro. Now, without further ado, let me pass the baton to Alvaro first. But let me do that by asking one random question just to set the stage somewhat informal for both speakers and audiences. Okay, here is random questions. For both of you, the Toby and Alvaro, if you were the CEO of DeepMind, what would you do? You may not want to be a CEO, but if you just imagine it. Anyone? And Alvaro or Toby?
That's a tough question. I mean, I would say I'm not in a position to answer it, because if anything, I'm kind of like learning a lot by being in DeepMind about like what a company can care about, and especially, you know, how important it is for companies to care about applications of the actual work that they do in the real world to solve important problems. So like, if anything, yeah, I don't think I'm nowhere even close where I could actually put myself in that situation. But I am learning a lot from what I see the CEO of her own company do. So yeah, that's my answer. Maybe that's not what you expected, but.
How about Toby?
Yeah, this is actually a tough one. Yeah, I don't know. Like DeepMind has a lot of very different things they do. I mean, I don't know. Like, I'm personally, I would be very interested as an imaginary DeepMind CEO. Kind of, I mean, they obviously like push the directions I'm interested in more, right? But like, I mean, it is kind of cool that there are so many different things going on currently. I mean, it would be very interesting to see like more like, I don't know, science and engineering applications. But I mean, we're doing that in other ways already. I don't know. I don't have a good answer.
Okay. Well, today's random question was tough question. Okay, the Alvaro, please.
Okay, thank you. So yeah, hi everyone. My name is Alvaro Sanchez, and as Yongshu was presenting me, my research engineer at DeepMind, and today I will be presenting with my colleague Toby, who is a research scientist. So we will talk a little bit about our research on learning simulation using graph networks. So the work that we're presenting here was done in collaboration with our great colleagues Meire Fortunato, Jonathan Godwin, Rex Jean, Jude Leskobek, and Peter Battaglia. And in this talk, we will actually try to solve the results from our recent research, including some high-level insights. But we will also explore some of the design principles behind our models, including some more in-depth detail about how graph neural networks work. So we hope we will have something for everyone, independently of the level of machine learning expertise. Plus, if you find the model section maybe too low level, there will be some nice videos for generalization examples towards the end that we hope you will enjoy. So overall, we believe simulation is fundamental to science and technology. But the first important question is, why we would want to learn simulation at all? So the most common argument here is the speed. They're pretty well-engineered solvers. However, they're usually very computationally expensive. And because they require taking very small time steps and very high spatial resolution, mostly so they can approximate the derivative. So this is what makes them expensive, that they have to approximate kind of like perfect spatial or temporal derivatives. And these limits that are there for classical solvers, they don't necessarily apply to machine learning models, which can often learn subgrid dynamics or compensate for large time steps or large spatial discretizations. But beyond this, there are less obvious reasons why it's a good idea to learn simulation. Like, for example, neural networks are often differentiable, and they have smooth gradients. And this can be immensely helpful for solving inverse problems, such as optimizing the shape of an airfoil, or for like an optical control problem, optimal control problem, sorry. And sometimes we don't even know the exact model of equations of the parameters of a system that we want to solve. So running the exact simulations is hard. If you think, for example, of climate models or like modeling frictional contact in robotics or stuff like that. And finally, writing simulators is hard, and even harder if you want to write them for accelerators or for GPUs or for TPUs. So distilling models into a learned model that can run well on a modern accelerator can be very useful too. Now, this sounds so great. And when we are used to kind of like seeing news and headlines about machine learning, usually we say things like, 2 billion times acceleration. And this sounds amazing. But actually, if you start digging more into detail, actually, a lot of the models that are behind these headlines, they often look like the one on the right, where you maybe have a few input parameters that you feed into a black box neural network, which then outputs a single number or maybe a curve or an image. And of course, the inference time for this neural network is probably just a few milliseconds. So if the number you're regressing is the output of a climate model that normally runs on a supercomputer, you very easily get a 1 billion factor improvement. What is actually a bit less clear is whether the model has actually learned anything at all about the actual physics or about the actual system. In most cases, it's probably just fitting and interpolating a curve. And neural networks are very good at nonlinear interpolation. So this is not necessarily bad when it works and you can train the model. But we know they are usually bad at extrapolation. So for example, if you have a model predicting the flow around an airfoil, and then you try to learn on a lot of samples where the airfoil is between 0 and 10 degrees inclination, and then you try to test this model on a 30-degree inclination, the model will usually not give you a good prediction for this, like most of the models that people are used to. So you really need to make sure that the input space during training covers a kind of like representing range of the inputs that you expect to be able to test on later. And because you need all of this training data to be representative of any possible future inputs, now you have to run tens of thousands of expensive simulations to generate training data. So you can later maybe run 10 cheap simulations on this very narrow set of parameters. And it gets worse. If you want to learn like a full model of a typical general purpose engineer simulations like COMSOL or ANSYS, there's no way that you can build a data set that even begins to cover the whole input space of the things that you could simulate with it. And of course, now the situation of the billion-time acceleration starts to look a bit bleak compared to the headline. So our current research is focused on exactly this issue. So we try to train models which actually learn reusable knowledge, something like physical laws that allows them to then be applied far outside the data that it was trained on. And we do this by structuring our model right. So we can actually get such strong generalization along with kind of like a lot of like nice the reservoir properties by really imposing inductive biases in our model. And like you can actually get things like scalability, stability, speed, versatility of the model across domains. So in general, most of what we're covering in this talk today is work from our 2 recent papers from ICML 2020 and ICLR this year. And we'll also be playing a few videos. They will probably look a bit choppy over the video call. So if you look at the project page links on this slide, you can actually look at the videos live. But keep in mind that like what we're doing is still basic research, and these problems far from solved. So we focus on generalization, but there's lots of other angles that you can study learn simulation from, such as accuracy, convergence properties, and of course we focus on kind of like an end-to-end learned approach to learning. So you don't have to know a lot about the system you're learning, but of course combining learned components with hard code solvers is also a completely different area with its own benefits and challenges. So before I tell you about like how our model works and talk about generalization, let's look at the kind of things that we can do with it. So these are rollouts of our model trained on particle simulations of water, sand, goop, with the particle representation that our model is working on the bottom and a rendered version on the top. So here's a very different simulation. Now here we have flow from left to right around a cylinder. So color is the velocity field, and this is on a 2D triangular mesh. So you can see that it's very hard to see the difference between the model prediction at the bottom and the reference console simulation at the top. Here's a compressible flow around the cross-section of our airfoil. And you can see that our model correctly captures things like shocks and vortex setting. Or something a bit different, maybe like closed dynamics on a moving dynamic mesh learned from a computer graphics simulator. And in this case, you can see even the triangles adapting during the simulation. And this is something that Toby will talk about later, too. And finally, also a deforming plate, now on a tetrahedral mesh. And this is also a quasi-static simulation, as opposed to the inertial simulations before. Now, the interesting part is like all of these simulations that we've shown, they are learned using the same model with the same architecture, whether it's 2D triangles, particles, or 3D tetrahedra. So this is what we find very interesting about the model, that a single model can do all of this with virtually no changes to the model. So without further ado, let's actually start looking at how we're doing all of this. So what we do is we learn a next step prediction model. This is a model that takes the simulation state at the current time step and predicted state at the next time step. So the model is an encode process decode graph network. So at high level, at every time step, we encode the system state into a graph. Then the neural networks process the information on that graph, and then they decode back the updated system state. And all of this using reasonable general purpose components. Now, our main design principle behind all of this general purpose inside these neural network components is this. So essentially, recognizing that neural networks have issues with extrapolation, then we can actually make their life easier by recognizing what the problem is here and try to design components that would make them better at extrapolation. And giving machine learning a little bell is not very unfair. Like help is not very unfair. So one of the most important things that Sir Isaac Newton acknowledged is that he was standing upon the shoulders of giants, and that he was not starting from scratch, but benefiting from all of the work that came before him. So in general, we found that it is very useful to give neural networks the opportunity to do this. And the way we achieve this is by adding inductive biases to our networks. So an inductive bias is anything that allows a model to prioritize one solution over another. So if you want to say this differently, Can you still hear me?
Yeah, I can see your slides and I can hear you. Yeah.
Yeah. So
oh, I don't know what
yeah.
happened.
If you want to say this differently, inductive bias from a Bayesian point of view, it's a way to give our model a prior over what to do in the absence of data.
Alvaro, somehow we cannot see your slides.
Okay. I think someone else shared the screen for a second. I'll share them again.
Oh, okay. I see.
Yeah. Can you see them now?
It's starting to share contents. So yeah, now. Okay.
Perfect.
Let me say a word to audience. Please do not share anything except the speakers. I wish I know how to prevent that. Okay, please go ahead, Alvaro.
Okay.
Sorry about that.
Yeah, no problem. So essentially, we usually find that models with the strong inductive biases are much more data efficient and can generalize much better to unseen scenarios. So let's look at a simple inductive bias. Imagine we're trying to model the position of this falling piano using a black box neural network. Now, the first thing that we can consider is to use a neural network to produce the next position of the piano, given the previous position and velocity. And a model like this one will have to spend training time and possibly capacity just to learn that usually the position of the piano at t+1 is close to the position of the piano at the previous time step. So instead, we can ask the neural network to predict the difference between the previous position and the next position. Now, the model prior will have it very easy to indicate that the piano will remain on the previous position just by having the neural network output 0. But of course, we can take this one step further because we know that this system is actually driven by inertial dynamics. And in the absence of forces, it's not really position, but velocity that remains constant. So this model will still have to learn that a piano moving with constant velocity will in most cases continue moving with that velocity. So instead, we can ask the neural network to predict a correction to the inertial trajectory. So this way, if the neural network outputs at 0, then the object will continue moving with constant velocity. So now this model has an inertial prior, and the neural network can focus the learning and the capacity to actually learn the non-trivial parts of the dynamics, like, for example, the effect of gravity or the effect of air friction. So what we do is we add many useful inductive biases like this to our model. And these are inductive biases that are well known to be very general in many problems. One of them, for example, is spatial equivariance. This is kind of like saying that if we place this box 1 meter to the right, the physics should be the same that where they were before. Or local interactions that, like, maybe particles are often more strongly influenced by particles that are nearby than particles that are farther away. We know that if we were to place this kind of like box 1 meter to the right, then the physics will be the same according to kind of the first inductive bias. So I'm not kind of like to go into the full set of into inductive biases that we have here, but we'll illustrate kind of like a few to give you an idea of like why we constructed a model in the way we did it. So first, we're mentioned that like we're using graph networks, and we will see that graph networks are a type of neural networks that allow to very naturally express many of these inductive biases. So let's actually see how graph neural networks work. Imagine we're working with this gravitational system. And many of you will be familiar with the simplest of neural networks, the multi-layer perceptron, which takes a vector as input and returns a vector as output. So we could put the position and velocity of each body into a vector and feed it through the MLP. The problem is that by doing that, we're imposing an ordering. So if now we were to ask the neural network the same question, but giving the inputs in another order, the answer will not be guaranteed to be the same. So the MLP has to learn the interaction of all of these bodies separately just to eventually figure out that gravity works in the same way for all of them. A better representation than vectors for a system like this one are graphs, because by definition, nodes and edges in a graph don't have a specific ordering. And in these graphs, maybe we can still have each node represent an object and store some node features such as the position, mass, velocity of the particles in those objects. And we can also store features in the edges connecting the nodes. For example, something like a spring constant if the particles are connected with springs. And finally, we may also have some global context that affects all of the particles, such as like the gravitational constant if we want to change it between simulations. So now all we need is a neural network that is able to operate on these graphs. And this is what graph networks do. A graph network simply takes a graph with node, edge, and global features and updates all of those representations. So we can, for example, ask the graph network to produce the position of a node at the next time step. The magic is that all of the updates that the graph network does happen in a permutation equivariant way, independently of the order in which we specify the nodes and the edges. And this is possible because graph networks work based on something called message passing. So let me explain in detail for those of you that are not familiar with this model what message passing is. Let's start looking at a single edge of the graph. So for that edge, we can build a vector by concatenating the vector feature of that edge, the vector feature of the two nodes that are connected by the edge, and the global vector feature. And then we can apply a neural network to this vector to compute an updated vector associated with the edge, which we will refer to as the message. And we know many forces in physics are typically defined as pairwise interactions such as this. So we can actually think of pairwise messages as an inductive bias. Now, we actually repeat the process to update the representation for all of the edges, but using the same neural network. And this also imposes a prior that the update function should be the same for all of edges, similar to how the laws of physics are universal. After we have updated the edges, then we have to update the nodes. And now we do something similar. We start looking at one node, and for this node, we take all of the messages that this node receives using a sum. And this is closely related to the superposition principle in physics and how forces can usually be just added up. And of course, in this case, instead of forces, we will be operating over length representations rather than just forces, but the main principles still apply. And then once we have aggregated these messages, then we build another vector with the feature vector of the node, the aggregated messages, and the global vector. And again, we give this vector to another neural network, and then we use this to update the node representation this time. And note that in this case, a node can only update itself based on its neighbors. So imposing a prior, this is imposing a prior of local interactions. And similarly to before, then we repeat the same process to update the representation for all of the nodes using the same neural network. So these two steps is what makes the network kind of like equivariant to permutations of the nodes, because actually it doesn't care in which order you provide the nodes on the edge and the edges. So there is usually an additional update step, which allows to update the global features of the graph. But this particular update is not local. So for this work, we don't use it. But like, you know, in some of other work, you may be seeing that people actually use global updates. So now that we know that we will be using graphs and why, I will leave you with Toby, who will explain how these models are connected to our domains and actually go through the results and the generalization.
Let me share my slides. I think you have to unshare because my share button is grayed out. Oh, it's still grayed out. There we go. You see my screen?
Yeah.
All right. So yeah, thanks Alvaro for the introduction. So let's talk about how this actually works for a concrete system. So specifically, let's look at the encoder and what's happening there. So the encoder is a module that takes the input set of nodes and builds a graph. And then we can use it in the graph processor to process and pass messages on the graph. And so our model can deal with various types of systems. So we've shown that we specifically looked at particle systems and meshes. And so for meshes, building a graph is kind of a trivial operation, right? Because a graph, like a mesh is already a graph. So we have mesh nodes and mesh edges. And so we can directly use those to build a graph by just saying like every node in the mesh is a node in the graph, and every edge connecting these in the mesh is an edge connecting them in the graph. If we have a particle system, on the other hand, we can use the particles as nodes, and we can just connect them by proximity. So that means that we take a particle, and within a certain radius, we connect all other particles in that radius by an edge to build a locally connected graph. And then, as Alvaro mentioned before, we can encode features into these graph nodes and edges. So for this example of a particle system representing liquids, that would be something like each particle's position, velocity, and maybe a particle type. Is it like a liquid? Is it a boundary particle or whatever? And then we could use this graph and pass messages on it. But it turns out we can actually do even better than this. So if we don't encode the position directly into a node, and instead encode the positional difference between two nodes into an edge, then we get translational equivariance basically for free, right? And this is a property that we know that pretty much a lot of the physical systems that we care about have, and our network can then exploit. And there's a lot of other things that are really similar to what we can do. And I think this is just to give you the basic idea of why we're doing this. It's like we're trying to reduce the amount of information that a single neural network can see as an input as much as possible. So for example, due to using graph nets, we only need to reason about the local neighborhood around each node, right? And due to encoding relative distance and edges, as opposed to like the absolute position in a node, the network inputs will look the same for a similar neighborhood, wherever that might be located in the simulation domain. And so this property allows the model, for example, to be used on systems that are much larger and have higher position values than has been seen in training. And this is something we're gonna look at later more in detail. Okay, so this is kind of how we can build a graph. As Alvaro said, we can run message passing on this graph. And then as a last step, we have to kind of decode this graph and get back our next system state. And so this is the job of a decoder and updater. So again, let's look at this example we had from our liquid system using particles. And one obvious thing here, what we could do is we can just say like, we take the features stored in the graph nodes and just add an MLP on that, and then decode that into like, say, the next position, right? But as Alvaro already mentioned earlier, this makes the problem just unnecessarily hard. So in practice, we can predict something like an acceleration, exploiting the inductive biases of inertial motion. And this is kind of nice because what it means again is that if you just have a neural network giving you a zero prediction, it would just keep all the particles flying with their previous velocity. So that is a useful bias to exploit. And we only have to predict the deviation from that. So there's a lot of more to talk about, but I think like you get hopefully the basic idea on how we constructed our method and why we did so, right? So we encode a system into a graph, we do a message passing on the graph, decode back to the next step. And we try to pack as much inductive bias as we can in that process. And the beauty of all of this is that the actual core model can remain exactly the same for all of these different systems, right? Whether we simulate liquids or cloth or aerodynamics, and whether that's an inertial or a quasi-static simulation, or like if it's particles, triangle meshes, tetrahedra, what do you have here, right? So the only thing we need to do different for these systems is how we actually encode or what quantities we encode and how we decode them. So we've already seen, for example, that for particles, we can encode node positions and decode two accelerations of these particles. But if we have, for example, a continuous field, like these velocity fields in the Eulerian fluid simulations on the right, we can just encode the samples of the velocity field at the mesh nodes into our graph nodes. And then we can decode the changes in these fields, right? Or if we have incompressible flow, then we do the same for a density field in addition to the velocity field. And so like, it will come to no surprise then that what this basically amounts to is learning the right-hand side of an underlying PDE of these systems, right? And we're not only learning the PDE, but we also learn all the nasty implementation details surrounding discretization schemes, parameters that you might not want to encode, global effects like pressure, like everything basically that makes writing classical simulators hard. That's all learned in our model. The only thing we have to deal with is getting our variables out and updating them. All right, so this is basically how you learn a next step model. And once you have such a model, you can use it to make predictions. So because we are learning these temporal simulations or dynamic simulations, what we do is we unroll our model to get a simulation trajectory, right? But it means we start with an initial state, and we apply our model to this initial state, and we get the next step. And on this next step, we evaluate the model again until we get like a rollout that we can then render, for example, as this animation or look at in some other way. And so it's actually kind of surprising that this works at all, because normally what happens if you train a model on like predicting the next step and then unroll it for hundreds of steps, you will get something like the animation on the right, right? So these tend to explode. And the reason for that is error accumulation. And so even if you have a model that's very accurate, there will always be some slight imperfect predictions, and further steps will compound this error. And this is something that's not particularly surprising. It also happens in classical solvers as well. And this is why we all have these fancy integration schemes. But this is much, much worse for learned models of dynamics. Because eventually what will happen is that the accumulated error can form states that haven't been seen in training. This is particularly true for things like physically invalid states. So here we have an example of like particles getting too close and overlapping. Or it could also be things like divergences in incompressible flow, anything that hasn't been seen in the training data because it can't be for this physical system. And because neural networks are dumb, as we mentioned before, and they don't extrapolate well, given such an input they haven't seen, they will give us a very random prediction. And particularly often it leads to these exploding trajectories. So often what people do is things like training over multiple steps. But what we found is much simpler and works a lot better is using training noise. So what we do is during training, we corrupt our input data with Gaussian noise and ask the network to compensate for it. And this way the network can learn to like see these states which are slightly deviation from our like training set input, but also they can correct some physically invalid states, for example, such these unexpected divergences, right? So let's have a closer look at one of our rollouts. So this is the rollout, again, train on one step, and we unroll it for a few hundred steps. You notice there's definitely no explosions here. But also, like, even in this very chaotic regime, we actually remain pretty close to the reference simulation on the right at all times, which is also kind of interesting to see. And so this is a rollout of a few hundred steps, but that's not necessarily the limit, right? So you can basically unroll indefinitely. So here's an example where you just keep unrolling for, I think, 40,000 steps in total. And you see like the dynamics just keeps being the same, so we don't have any like super bad buildup of error. And again, this is just trained on next step prediction as before. Okay, and yeah, now finally, I think we should talk about generalization, which is kind of the thing that motivated a lot of our work. So for that, let's look at this simple example. So we have a model that we trained on this little 2D domain on the left. So that's the only thing that's in the training set. We have a set of like these single water cubes, which fall onto a randomized line obstacle. And there's, some variations. The cube might be slightly different size, or this obstacle might be slightly different orientation or position. But that's kind of all there is. But then at test time, what we can do is we can take this model and we apply it to a very different scene, right? So first of all, we have a bigger domain, and we also have a continuous inflow. And you can immediately see that the dynamics that we get here are qualitatively different from what we have on this training set on the left, right? So neither this continuous inflow nor these water vortices have been observed in training at all. And this is exactly the type of generalization that you really wouldn't expect to get with like a learned model unless you construct it particularly to do so. But we already know kind of why this works. And this is because of all of the inductive biases that we have built into our model, as Alvaro explained earlier. So for example, each node in the network only sees a particle in its local neighborhood, right? And even if we have a very different dynamics on a global scale, chances are that a similar neighborhood has been actually observed in training at a local level. So for example, we have seen like the dynamics around water surfaces, or like how particles interact with the box boundaries, or the dense blocks of water just move around. Oops. So due to all of the locality invariances, the network inputs for all of these little neighborhoods is kind of, they actually look kind of the same. So it's not surprising that the neural network can actually give us a good prediction for those. And the effect that it has is that it encourages our model to learn local universal laws, something that's very much like the actual underlying physics, as opposed to overfitting to some more global feature of the training data, which is something you see often in learned models dynamics. All right, so let's look at a bigger example. So this is an example on meshes this time. And again, we have a training set. That's this box on the left corner. So we have just a bunch of variation of these rectangular flags. And then at test time, we applied on this very different windsock with tassels. And so, I mean, the shape is different. It has never seen the cylinder, but also this mesh is much bigger than the training meshes, right? So we have 10 times as many nodes. You can see all the little triangles here. And again, like this is a close up here with the training and the test domain side by side. And so the fact that we can actually run these simulation at test time on much bigger scale is actually also quite interesting by itself, right? Because what it means is that our training data doesn't necessarily have to be expensive, because that's a point that's often made about that you have to like balance the cost of like training a model versus the thing that you can use it for. But like with this kind of method, you can actually train on cheap lowers data and then at test time scale it up to something more complex. All right, as a last point, let's look at meshes. And this is relevant because a lot of simulators like finite elements, which are very popular simulators in engineering particularly, they use meshes as representations. And that's for good reason, because I mean, a lot of domains like the ones here, you could represent them as like voxel grids, but it's not particularly efficient to do so. And also, if you operate on meshes, there's a lot of nice tools from continuum physics that you can exploit to give you nice solutions to these PDEs that you're solving. But the fact that we are working on things like meshes and graphs is actually quite unusual in the field, because the vast majority of machine learning research for physics prediction does that on 2D regular grids. And that's, of course, because these well understood convolution architectures like ResNets and UNets are very prevalent and well understood. So a lot of people just use them. But also there's a bit of an impression that learning on graphs only works for small systems. And one other point we're trying to make in our research is that that is not actually longer true. So learning on graphs can actually scale. And know that we can use meshes and graphs as representations, we might as well do so and reap all the benefits that these representations bring us. And these are exactly the same that they bring to classical simulators. So here's an example of one of these nice advantages we get using meshes, and that is just adaptivity, right? So this is one of these aerodynamic examples that Alvaro showed you earlier, the flow around an airfoil wing. And the whole simulation domain is 40 meters, but at this wingtip region, which is apparently very important for these simulations, we get sub-millimeter accuracy. And that's with a mesh of 5,000 nodes. If you were to put this on a grid, you would need a uniform grid of 40 billion nodes for the same precision. But we can take that even further. In this cloth example earlier, you might have noticed that the triangles keep shifting during simulation. And this is because the optimal triangle size we kind of want for the system will also change over the course of the simulation, right? You might want to have smaller triangles where these bands and folds are, which of course move if the flag blows in the wind. And this is actually something we can learn too, right? So what we do here is we learn a GraphNet model, much like the one we use for dynamics prediction. and we predict a sizing field, which is basically a spatial map which indicates where in the simulation domain we need higher resolution and where we can get away with coarser triangles. And this sizing field can then be used to dynamically adapt the resolution during the simulation rollout, but by passing it to a very generic remeasure. And all of the cloth examples that we've shown you use this method, and it seems to work very well even in the generalization setting. Here's an explicit example where you can see the sizing field and the simulation side by side. You can kind of see that like where these bends and folds appear and propagate by the wind blowing the flag, there will be smaller triangles appearing in the mesh as well. All right, I think it's time to wrap up our talk. I think the general message we have for everyone is that straightforward application of deep learning to simulation often results in models that don't do so well on generalization particularly. But it is totally possible to construct models that do generalize, right? And we believe the key to do so is carefully constructing them with inductive biases in mind. And in particular, I think, I hope we convinced you that graph and mesh representations are a very powerful and promising way forward for learning the dynamics of physical systems, because they have a lot of these nice properties that we want from a learned model. And as we said earlier, our research mostly focuses on these end-to-end learned models, but there's a lot of other things you can do in the domain of learning physical models. And for example, mixing learned components with like hard-coded solver components, or trying to interpret the networks you've learned and trying to distill equations out of it. And there's a lot of cool work in that direction. So like I put some links on this slide for you to look at if that's something you're interested in. And yeah, so finally, we believe this is really an exciting area to do research in. There's lots of more open questions and no shortage of hard problems to tackle, but we really feel like we're making some progress here. And we're really excited, particularly in looking more into adaptivity. We're also kind of curious how far we can actually scale these models up in terms of like real problems in science and engineering. And again, like there's these links to the website for these two papers again on the slide, where you can find like both the paper and also like all the videos that we showed here, which probably like didn't play it well over this video chat. All right, that's it from us. Thank you so much for joining.
Okay, thank you so much for the great talk, both for Alvaro and Toby. We will have a Q&A session. We have a lot of questions, by the way. Okay, let's start from the beginning. Okay, the Rob asked, how do you deal with nodes that have a higher degree than other nodes? Wouldn't that change the size of that local node vector?
So in principle, because of how the node updates work, we never look at a whole neighborhood and put that into a vector and give that to a neural network. What we do is we look at all of the edges one by one, and the edges always have two nodes. And then when we update the node, we take all of the edges and then we sum them. So like that sum, the size of the output of that sum is the same regardless of whether you have one neighbor or you have 10 neighbors. And there's a lot of research that, like, you know, some other people sometimes take the mean instead of the sum or the max. In principle, the sum is the most powerful one, but for some applications, actually taking the mean is better. The only important thing is whatever op you take, you want it to be permutation invariant, because you don't want the output to depend in the order of which, you know, you maybe specified the node. So the sum is commutative, so it's kind of like permutation invariant by definition.
Okay, Toby, do you want to add anything to that?
No, I think that's exactly it.
Okay, thank you. Next question is by Fadi. How do you ensure conservation law? For example, mass, momentum, and energy conservation. Are they satisfied in the system you are studying?
I guess the simple answer is that they're not. There's like, as Alvaro most mentioned, there's a few inductive biases we put in. Energy conservation specifically is not something we did put in, right? So there's like some drift we can get in these variables. In general, we found that if we do it well, they are not too bad. So like certainly, like if you look at the simulations, there's no kind of explosion in energy, for example, as like you will have in a lot of solvers where integration goes bad, right? But there might be drift in things like accumulating divergences and things like that. And I mean, this is something we're interested in, like exploring a bit more what you can actually do to give you better guarantees on these things. I think, I mean, currently, what we do is kind of, you kind of want to try to do two things with the model, unless you specifically have something built in that guarantees you that, which is if you drive your model error low enough, and also you, through, for example, training noise, give your model inputs that a little bit out of the training range, you kind of are making sure that you don't get any crazy results, right? But you don't necessarily guarantee anything beyond that. I'm not sure if you have something to add to that, Alvaro.
Yeah, not much. Just say that like there's different models may make different compromises. So like even simulators, when we say a simulator conserves energy very well, often it does so because it compromises with something else. Maybe it has a constraint satisfaction stage that it kind of like is particularly targeted at energy conservation, and by solving that constraint is actually moving something else that could have been like better in a different way. So like in that sense, we also know how to introduce this constraint into neural networks. We're just not doing it in these papers, but we will know how to do it, I think.
Okay, sounds good. The next question is by Mark. How much of the work is publishable and how much is proprietary?
I mean, everything we covered in the talk is published. So there's these two papers here mostly. So there's nothing super secret. I mean, there's more things we're working on, but we're not ready yet. But once it is, we will publish that. For the first paper, there's even code out, and like some of the, actually all the data sets and the code is out there. It's also like there's a link on this webpage on top. For the newer paper on the meshes, we're preparing a release for code and data sets, but it's not there yet. I'm how long it will take.
Okay, wonderful. All right, next question is by Matt. Do you have quantitative error metrics beyond the video, looking good?
I mean, we have some, I mean, so it's like always a little bit hard to measure quantitative error on these like dynamical simulations. So, I mean, we did the obvious thing, which is we measure one-step mean squared error for all of these. And we also measure the error over like a window of time steps, right? So like over the first 50 time steps or like first 100 or whatever, right? And these are indicative of certain different properties. And you can compare them to other methods. In general, like it is true that like the lower the error goes on, especially one-step error, the better like your rollouts will become. But like certainly especially for chaotic systems, at some point these errors stop making sense, right? Because even like a small perturbation at step one will like down the line then give you a very high error, even though the behavior is completely reasonable. And this is something that's also true of classical solvers, right? And there's probably other metrics you can look at, like statistical models, like looking at like energy over frequencies and stuff like that. We haven't really done that.
Okay, next question is by Kyle. For a granular system where the locally connected grains change as a function of time, how do you handle creating and destroying edges?
So for the edges, we just use a spatial hashing algorithm for computing the nearest neighbor distance within a certain radius. We never try to optimize that part of the code too much. So actually, we were recalculating everything at every step. So in principle, edges just come and go at every step after you compute the next positions. Then in some of the simulation, we actually add particles in the middle of the simulation. And we also remove, I don't remember if we remove particles in any of the demos. I don't think we do, but like in principle, that's not a problem. Because our model only takes a single step of inputs. It's just a transition model. It doesn't have a recurrent state. You can very easily just like add more things or remove things, add edges, remove edges. You can just like have that flexibility usually. And in the mesh one, for example, we're just recomputing the entire mesh and reinterpolating the positions, and that works fine.
Okay, thank you so much. Oh my goodness, the questions are pouring out. Okay, it's almost out of control. Okay, the next question is by Yasaman. How much of the computational cost do we save with graph networks versus numerical simulations using physics-driven models? Okay, who's going to answer that?
This is also something that's a bit hard to measure. I mean, now in your paper, we have some performance comparisons. So like generally, like, especially if you have a numerical simulation that's very expensive, you can get a lot of gains. So, I mean, we have numbers, we like just like end-to-end walk log time 10 to 100 times faster than the reference simulator. But it's always a little bit tricky to compare that. A lot of these simulators don't have like GPU accelerated versions, for example. But I think like one of the points that's worth mentioning here is, I think this is kind of like one of the benefits a model can give you, is that in areas where it's really hard to have a very fast handwritten solver, these models can shine particularly well, right? So like if you have just a very simple domain, you have like, I don't know, a box with fluids, and you have periodic boundary conditions, and there's very fast solvers you can use to solve that problem. It's like a learned model might not be necessarily faster there. However, if you have a very complex domain, which is the case in a lot of these engineering applications with complicated meshes, boundary conditions, whatever, like a lot of these nice properties that traditional solvers like multi-grid solvers or whatever have kind of break down the more complicated the domain becomes, right? Versus a neural network model can actually learn very, very nice approximations to like still give you large speedups here. And this is the same is true also for time. So like our model, for example, you can kind of learn something like an internal fancy integrator, and we can take much larger time steps than a classical solver, right? Because all of these traditional things like CFL condition or whatever don't necessarily apply to our model, because it can kind of look at more like bigger coherent structures and not necessarily only at like the single cell level.
Okay, thank you. The next question is by Xiao. What is GNN's superior to CNN? Can you briefly explain when we want to use GNN instead of using CNN for image-to-image prediction?
So that's a very interesting question. So like, I don't think CNNs or DNNs are really opposed to each other. Often we actually often use CNNs for like some of the work that we do. Actually, recently we published something in a workshop in iClear. Let me share the link here. So this essentially, oh, actually that's meant to be 2 links, but it didn't. Yeah, there you go. So essentially, this added, this work that we did modeling PDEs, and we were modeling PDEs on grids in this case. And for this work, we actually used convolutional neural networks because we found they were sufficient for that domain. And actually, when we tried graph neural networks, they worked fine. But you know, graph neural networks tend to be a bit more expensive to evaluate. So what I would say is, if for your application a CNN works fine, then I will not discourage people from using CNNs. If you suspect your model doesn't have enough, like, you know, reasoning capabilities, then there's a whole spectrum from like a CNN, a transformer, and a graph neural network that you can start exploring. And you know, in a way, like graph neural network is the one that can model the interactions in the kind of like in a way that is closer to how like most simulators model interactions. So like, is this a continuum of models really, and you should just pick whatever was best for your application. So I wouldn't, I don't kind of like play. I just think overall, if you don't know what's gonna work and you want to invest on one, then you can jump to the graph network, and usually it will work. And it gives you flexibility for like, you know, non kind of like non like uniform grids. But overall, yeah, like unless you have like long range dependencies that are very hard to reason about, and like using kind of like a convolution sort of approach, I wouldn't discourage people from trying CNNs for their problems. Yeah.
Okay, thank you. The next question is by Charles. Would you comment on why the error in your flag wind simulation predictions plateau as time grows? In your paper, I'm particularly interested in having low errors at some final time, and I'm worried that using the update from previous time step to next time step will propagate the errors. Thanks for the talk, by the way.
So that's very similar to the point raised before on like how that it's hard to measure error. So I think for this flag particularly, what we see is the coherence error, right? So what I mean by that is like the error that you see at the plateau is if the flag that we have and the flag in the reference simulation all in a different angle, right? Because like the little differences in the first few steps made like the flag just like swing into a different direction, right? And so like at these long ranges in our simulations, that's like often after like 50 or maybe 100 time steps, like most of the error measures decoherence. The main thing that we wanted to show with this graph is that the error doesn't increase beyond that, right? So we don't have any uncontrolled instability. So the only thing we have is that this kind of like chaotic behavior accumulating over time. And so I don't know if you're looking at like more. So yeah, there's two things. Like one, it's good to know that it does plateau, right? So there's no explosion. The other thing, if you actually want to compare more, like what's a more accurate model, you may want to look at just like MSEs in very short time horizons. So like just the one step or like the few step error. This is much more indicative of the final performance there. And the other thing is you can do like you can again like start looking at these kind of more, I don't know, domain-dependent statistics, right? So for cloths, you could look at, okay, do your triangles actually stretch at some point, right? Or for incompressible flow, can you see like, oh, do you actually have any singularities or divergences that appear over time? It's stuff like that, right?
Okay, thank you. Next question is by Xiao Yu. Well, it's just a comment he made. The graph is a good idea for mesh-based modeling compared to CNN and LP. It is a good choice for simulation based on FEA, graph element network. However, personally, I feel most of the papers are just fancy ways to approximate finite difference or finite volume. Imagine if you have a poor scheme, poor mesh, it is still able to tell you something about physics, even though it might be incorrect. They behave much like the prediction result you have, but since you have data to correct the model, dissipation is less. And would you respond to this comment?
I'm not 100% sure. Like I understand it fully. I mean, if it's about triangle quality, yeah, I think there's interesting things we can do with like learned models. And I mean, classical solvers have really strong dependence on like good, well-conditioned meshes, which for the learned models, it might not necessarily be true. We haven't really tested it because, I mean, in the end, you also need training data for that. And so like, you have to think about how to generate training data for like bad meshes so you can actually deal with those at test time. But I think like fundamentally there's probably much more you can do to compensate for stuff like that. I think there was probably another element in this comment. I don't know. Did you pick up on something else, Alvaro?
Yeah, I'm not sure like the part about the dissipation, like what it like sort of like what I find is that like neural networks are like very good at producing like high contrast outputs. Like for example, in this other paper that I was kind of like mentioning before, we found that like if you take the same simulator and you run it at like lower spatial resolution, then it gives you an answer that like it still has like the correct physics, but maybe it's much more affected by numerical viscosity. So kind of like our model, you can use it just to model the entire system, or you could maybe just use it to correct the other model and compensate for numerical viscosity. So in this sense, our models can be very good at this, and this is why the videos look good, because the neural networks are good at producing states that look like the real state. And I think they can be complemented easily with like other models. And probably for science, for actual like scientific applications, in many cases the kind of like winner combinations will involve combining them with something that that has nice properties, or maybe tells you something about the physics, even if it's not correct, and then use the model to correct that if you want to have more guarantees.
Okay, thank you. The next question is by Piyush. Any thoughts on graph level predictions? Any specific type of models that work better in those kinds of problems? Should one use global node readout or MLP on aggregated node edge features?
Yeah, so to answer this is a very interesting question, and in lots of applications you don't know which one you should use. Now, the main problem here is that like often when you work with graph networks, you want to generalize to larger graphs, and if you actually have a global component in the graph that can communicate to everything and then a single output, then it can be very easy for the model to overfit to the sizes of the graphs that it was trained on. So when you generalize, you're planning to generalize to graphs that are larger, I usually recommend to try to not use a graph network with globals. Keep like pure message passing, and then have all of the nodes or all of the edges contribute via a linear operation to the answer in a way that when you scale to the graph, maybe it will just be a linear operation. So there will not be a neural network that will get surprised by receiving like the sum of 40 elements, where on train time it only saw 20 elements. But this is a very interesting question. It really depends on the application, and I think it's one of the big challenges. So something else that people have tried too is you can use a different aggregation fraction for the globals. You can use something like a min or a max or for the globals, which is less sensitive to the size of a system. And then for the messages, you continue using a sum for the node aggregation of messages. So it's really like a very interesting question. And I'm afraid, beyond that intuition, I cannot really give you a rule of thumb, because there's no right answer. I think it depends on the application.
There's also another approach that sometimes people take, specifically for things like point clouds or like stuff that has geometrical structure, which is you take your whole graph and then you have a downsampled graph and you connect these edges and you kind of go down level by level, similar to like CNN models often like converge down to like a very low, like step by step to kind of a lower resolution. And in the end, you read out on those nodes, right? So like DG, CNNs and stuff like that do that. And there's a lot of like shape models do similar things. And I think the idea is that you can capture both local and global information this way better. But it really depends what you're doing, as Alvaro said.
Okay, thank you. The next question is by Bakxiong. For a chaotic system, is the simulated state space same as the ground truth state space? Is it possible to pose some state space level constraints as useful inductive biases?
I'm not sure I understand the question.
Bakxiong, if you're there.
Yeah, if you want to just.
Yeah, do you want to unmute yourself?
Yeah. So I think to answer the question, we're not modeling on latent space. So when we do kind of like one-step model, it's always going from the ground truth state space, like spatial coordinates in the real world, back to spatial coordinates in the real world. Like another option would be to have a model that like does what we will call a latent rollout, which is you do the same thing without going to back to the spatial world. In practice, we find that like we didn't need to do that. So it was easier to keep it simpler, but just going back and forth from the real world all the time. Was that the question?
I was wondering that we are just using the mean square error as some guidance to train the network, right? And this might not provide really informative guidance to learn from one step to a next step. And in a chaotic system, so we have all the state estimations, and we may generate a PDF of this whole trajectory of the simulated system and the original system. And would they match? If they do not match, can we use this as some inductive bias to constrain the network?
Yeah, I mean, there's certainly a lot of other things we can do. I mean, we haven't really experimented with any of that. I mean, we mostly use L2, like direct L2 loss, because we know that's easy to optimize. I mean, even with that, I mean, you can also do that not necessarily on things like position. You can also do that on other things, the system has, right? Like for turbulent system, I'm not sure like necessarily what's the thing you want to constrain your learning by, but like certainly for like, I don't know, for fluids, what a lot of people do is say like, oh, well, I know if it's incompressible, I know my divergence is 0. So I put that in my loss, right? And there's like a lot of other stuff you can add depending on information that you know of your system, right? And so we didn't really go into that game very much, but there's certainly like a lot of application-specific papers do that.
Yeah, thank you. But a question is that many of the efforts are going through the simulating part. What about like if there any adversarial training using graph neural network trying to provide some other guidance beyond L2 norm?
Oh, you mean like things like GANs and stuff?
Yeah, like graph-based GAN have some learn loss function in graph neural network. Is there any progress in that direction?
not super rare. Do you know a bit more on that, Alvaro?
I mean, so far, like our approach has kind of like been the opposite. Like we've several times in the past discussed the idea of like using GANs for a simulation, but like it was kind of because MSc was working fine. We didn't want to kind of like make our lives hard, but like having to train GANs, which are very well known to be like much harder to train. But there's certainly, when we think about like how we will extend these models to stochastic systems, GANs are definitely like one of the options. And we have like tried some things in the past, but like we haven't really explored that direction much.
Okay, thank you.
Okay, thank you. The next question is by Francesco. Have you ever tried to use inductive biases based on invariance to Lie group transformation, group CNN, or other differential geometry notions, geometric deep learning in general? What is your opinion on this matter? Do you see possible future developments there?
So we have played with these ideas a little bit. The answer is a little bit similar to the previous one. For the sort of challenges that we have set ourselves so far, we didn't have to go into these directions. We anticipate, actual like, more kind of like powerful geometry representations inside of neural networks could actually pay off once you actually want to generalize more from like, low data regimes to large data regimes. And, I think here we're actually talking about, inductive bias inside of the model, but like even something as simpler as like having a model that is rotational equivariance or, equivariant to like, whatever Lie group, rotations, mirror symmetries, stuff like that. It will only make the model like more data efficient too. But like so far we haven't found that like for the data that we had, this was really necessary. But it's certainly like very nice kind of like a research direction, and we would love to see papers published on this, and we would love to read them too. So
yeah, I mean, translation is the only thing we do, and that we got like a lot out of. I have to say, like we had initially just worked with absolute positions, and that's like all the generalization stuff is only possible because of that. A rotation is a little bit, I mean, yeah, it will give you a little bit less bang for the buck because it's very easy to do that with data augmentation. But yeah, all of these are very interesting directions.
Okay. Next question is by Matt. Have people cast traditional PDE solvers to use NN framework without any learning, just to use the high-speed GPU infrastructure? I don't know if this makes sense or is possible.
I think people are doing this, yes, and especially like now for these papers we use TensorFlow, and for like apart from TensorFlow we also use something that is called JAX. And TensorFlow is kind of like written more for machine learning, even though you can use it for this. But this other TensorFlow JAX is actually written not as a machine learning framework, but more as kind of like a distributed compute framework with GPU acceleration, TPU compatibility, all of this. So I think I don't remember any specific cases, but like in kind of like workshop talks in the past, I've certainly been seen people writing simulators using those machine learning frameworks. And yeah, I think it's a great idea, and these frameworks are written to be kind of like make using accelerators easy to people. So like very often, like I know some people that like write simulators and they maybe don't want to use JAX or TensorFlow because they don't want to have an additional dependency. But to me, the wins of being able to use that if you can is just like immense, because then you can write like a high performing simulator in Python. So which to me is amazing.
Yeah, there's like a lot of work on writing differentiable solvers without necessarily any like neural network learned components. Particularly, like one that comes to mind is PhiFlow from like Niels Thury's lab at TUM, which is like a differentiable fluid solver in TensorFlow. It's like, yeah, people don't necessarily write those so they are fast, even though that you can do that. They write them generally because then it allows you to put a little bit of a learned component in the middle of this whole solver, and then like differentiate through the whole thing and just like learn gradient-based updates for your little component. So there's a lot of work in that area.
Okay, thank you. Well, I would like to comment the follow-on comment. There's recently we have developed a nonlinear manifold with Houston model where we use the nonlinear the manifold solution representation as a neural net and then plug that into the traditional PDE solvers, and probably Matt or even Alvaro and Toby, you wanna check that out. Okay, the next question is by Dongil Shin. Thank you for the talk. Did you have any general requirements for the physics-based simulation models for training? In general, as the computational cost became cheaper than in the past, people in computational mechanics are trying to catch up with more accurate results using more complex simulations. Is this coinciding with the database that these data-driven modeling requires?
I'm not necessarily sure exactly where it's going, but I mean, for the way we picked the data, like our data sets to train on, it's like there's things that play more to the strengths of a model than others. So for example, like one very strong inductive bias we put in is that like interactions are local and message passing propagates information. And that's like true for like a lot of these like dynamic equations. But like if you have something that's like instantaneous or like even very fast, like long range interaction, this is probably a less good prior, right? And so like there's a little bit of that kind of requirement, but there's not necessarily much beyond that. I mean, you can kind of use whatever data you want to train this thing. It's just like some things play more to the strengths than others. I'm not sure there was another element to this question that I didn't get.
Is there anything you want to add, Alvaro? No? Okay. Okay. Next question is by Faye. The edge embeddings depend on the displacement vector according to the paper and do not seem to be explicitly rotationally invariant. Are the current GNN prediction rotationally invariant?
So the current model is not rotationally invariant, as we kind of like said before, right? Like answering the other question. So yeah, in principle, we've kind of like played with this idea, and like what we found is like there's kind of like a bunch of like rotational equivariant models out there. Most of them were kind of like designed for molecular property prediction, for kind of like, you know, low data regimes, because I mean, you know, when you're working with molecules, like any regime is like low data regime because there's too many molecules in the test set. So like in principle for this data set, we never needed to use this, but this is certainly something that we're interested on. And you know, if there's any particular equivariant model that you're interested on, I would be very happy to kind of like follow up on that if you want to share it.
I guess that's it. I think great job. You're the rock star. I mean, you banged all the questions posted in the chat room. Is there any other questions by? I mean, you can unmute yourself and directly ask those questions. If not, we can ask John.
Just one quick question. Toby, can you like comment on the difference and similarities between these graph neural network models and, you know, classic reduced order modeling, you know, model reduction, PCA, you know, like some of the work Doc James, Yarnay, Beach did, you know, like those real-time subspace simulation?
Mm-hmm. Yeah, sure. I mean, there's an obvious similarity. I mean, generally, like learned like models using neural networks and PCA, there's a little bit of similarity in that, like, yeah, you learn like a different type of space in which like your predictions are much easier to do it. And like, I think like specifically what's more similar to that kind of like reduced models is something like you just take your mesh or take your grid or whatever, you put everything into one latent, right? And on this latent, you do then prediction, right? And this is like a very low dimensional latent. And this is kind of like what I think there's a bunch of papers even combining with the PCA, but like you can think about as like a nonlinear version of PCA, right? And this kind of works. It has some advantages because it's nonlinear. Things like, especially like collisions and whatever, are often a bit hard to express with linear PCA. But I think like the main difference between our model specifically in these methods is that it's like not compressing everything into a single latent. We still exploit this exploit structure to a degree because we are operating on this graph and we're learning local rules on this graph, right? And this is something that gives you compositionality, right? Like this is the only reason why our models generalize at all. versus that is something that's really hard with PCA. I mean, it really only works if you have a very small set of dynamics that you want to learn and compress into like your PCA basis, right? Versus if you have some sort of like structure that you can compose, like this graphs, then it's much more likely to apply to in a very like an unseen scenario.
Okay, thank you so much. Is there any other questions? I guess. Oh, okay. There's one more by Paradeep. Do the results have any sensitivity to mesh scaling factor or mesh quality used during the training?
I mean, we haven't really experimented much with that. So we just took the meshes that our simulators give us, which are very different. Like you can see like the ones we got from Comsol are very regular meshes. Like the Cloth simulation gives us much crazier meshes that are much more like elongated. And I mean, we didn't have any problem with that. I think like, I mean, probably the limits for a neural network model are like actually like much higher than they are for classical methods anyway. So probably can compensate for a lot, but it's not something we necessarily tried much with. Yeah.
Okay, thank you so much. Oh, okay. Well, let's wrap it up here. I mean, it sounds like we can go on and on, but if you have additional questions, please directly, contact Toby and Alvaro. They provided the email address to you guys at the end, at the last slide, right? So please contact them directly. Okay, I mean, you guys did awesome job today with all those difficult questions. You really rock it. Let's thank our speakers for the wonderful the presentations and then wonderful Q&A sessions. And keep up the good work.
Thanks.
Thank you for inviting us. It was great.
Okay. No problem. Well, Toby and Alvaro, if you can stay a little bit longer. So there are some group of folks who is a real fan of you, right? So yeah, other than that, let's adjourn. Let me finish the recording here.